Okay, so this is the outline of this talk. So after a brief introduction, I will summarize our current understanding for neutron star mergers and the mass ejection. And then I'll present our latest result for the resistive emission simulation with a phenomenological dynamo for merger remnant. And then I will conclude for these specific topics. So yeah, first of all, I like to summarize why neutron star merger is interesting and invariable astrophysical and physical phenomena. Yeah, first of all, neutron star merger is believed to be a central engine for short gamma ray bursts because most of merger is likely to result in a system of a spinning black hole plus massive disk. And also, neutron star merger is considered to be a promising site for synthesizing heavy element because during merger, neutron-rich material could be ejected. And also, because neutron-rich matter are likely to be ejected, then ejecta could shine because in the neutron-rich ejecta, our process nucleosynthesis occurs and a bunch of the unstable heavy elements are likely to be synthesized. And then after the nucleosynthesis, radioactive decay occurs, and then in such case, ejecta could shine, like in the supernovae. And finally, also post-merger gravitation waves may carry information on nuclear equation of state, and this is a very important topic, currently very important topic for nuclear physics. And indeed, GW17 already 4 years ago has shown all these aspects. And so these 4 aspects are indeed shown to be real in the last event. So this is our current schematic picture for the current understanding for neutron star merger and remnants and signal. Anyway, so after the merger of binary neutron stars, so black hole or neutron stars are formed at the center. And typically, black hole or neutron stars are surrounded by the accretion torus or accretion disk. And during the merger process, first, dynamical ejecta. I will talk about this later. So dynamical ejecta ejected, and then post-merger mass ejection occurs. And associated with this mass ejections, so as I said that radioactivity part emission is likely to occur, and we believe that this shine in the optical and the infrared band. And if a black hole is formed, many of people believe that gamma ray bursts are also launched and gamma ray signal is emitted, and also associated with the interaction between the gamma ray burst and the interstellar matter. Subsequently, X-ray, optical, and radio, and so on are emitted. And in addition to these signals, because the dynamical ejecta has a very high velocity component, and then during the interaction with such a high velocity component with interstellar matter, so people predict that synchrotron emission occur. But this is not fully confirmed. So anyway, except for this, so many of the signals are already found in GW17. However, so this is just one event, and it's important to predict the next event. This is talks for my talk. And actually, there are many possibilities for neutron star merger and associated mass ejection. So this is a schematic picture for the possibilities. Roughly speaking, if total mass of the system, so small m, is larger than some threshold mass, a black hole is formed soon after the merger. And if mass of 2 neutron stars are approximately equal, so black hole is simply formed. And in such case, we don't have a strong emission after the merger. On the other hand, if a mass of 2 neutron stars are significantly different, so black hole is surrounded by disk for this case, and then so electromagnetic signal may be expected. On the other hand, for small total mass, in such case, after the merger, the so-called massive neutron star is a hypermassive or supermassive formed. And for the case of a hypermassive neutron star, after some angular momentum transport or cooling process, so eventually black hole is formed. And in such case, due to the angular momentum transport during the evolution of the hypermassive neutron star, disk is formed like this. And also, we have a possibility that supermassive neutron star is formed. This is a case in which total mass is very small. So say it's smaller than 2.5 solar mass, something like this. In such case, so we have the long-lived neutron star. But anyway, so also for this case, after the angular momentum transport process, disk is usually formed. And anyway, so there are a wide variety of possibilities, but typical remnant for binary neutron star merger is a compact object, so black hole or neutron star are surrounded by a disk or torus. And today, so I'll focus on the scenario for relatively small total mass case. So I mean that neutron star is formed and lifetime of neutron star is fairly long. Fairly long means that longer than the several hundred milliseconds. Okay, so next, so I'll summarize our current understanding for mass ejection scenario. So roughly speaking, there are two steps for mass ejection. First, soon after the merger, soon means that within the 10 milliseconds after the merger, dynamical mass ejection occurs due to the violent merger process. Subsequently, as I already said, that a typical scenario is that neutron star or black hole is surrounded by disk, and then so from disk via magnetic hydrodynamics or viscosity process mass ejection occurs. So I'll talk about this later in detail. And in addition to, so these are two mass ejection processes, but we also have the important process. One is neutron irradiation. In the presence of a massive neutron star, huge amount of neutrinos are emitted from the neutron star, and in such case, so neutron irradiation to ejecta is very important for determining the property of ejecta and the amount of ejecta mass. And also for the evolution of a disk, so weak interaction is very important for determining the property of the ejecta. So I'll talk about this later. And however, so I think that for dynamical ejecta, so our understanding is already so, well, not sufficient, but very close to sufficient. And by contrast, for our understanding for the post-merger mass ejection is still currently in a middle way. So first, I'll summarize our understanding for dynamical mass ejection. So for this, so many numerical relativity simulation has been done since 2013. And also for this, so we only need a fairly short-term simulation. And then so I believe that we understand well for this process. And what we learned in the last decade is that mass is about 10 to minus 4 to 10 to minus 2 solar mass. But for low total mass, so total mass means that so total mass is much smaller than the threshold mass for black hole, prompt black hole formation. This ejecta mass becomes fairly small, 10 to minus 3 solar mass. And the average velocity is about 20% of the speed of light. This is roughly speaking the escape velocity for this system. But during the shock heating process, some component could be very rapid, so rapid means 90% of speed of light. And the electron fraction is in the wide range. So for this process, initially neutron star has a fairly small electron fraction because it's very neutron rich, and the proton is a minor component. And then so initially, so neutron star matter has an electron fraction less than 0.1, but during the merger process by shock heating, so electron fraction increased to up to about 0.4. And this implies that our process nucleosynthesis, by the our process nucleosynthesis, wide variety of our process elements are produced, including the lantanoids, which is very important for determining the kilonova property. And also, one important thing is that this quantity depends strongly on the equation of state and the mass of neutron stars. So anyway, these are, I think that we well understood the property of dynamical mass ejection. By contrast, post-merger mass ejection is more complicated, and our understanding is less. So anyway, but I believe that we are by 70% understand that how matter is ejected from the post-merger remnant. So anyway, one key is that the neutron star is magnetized and the remnants are magnetized. And in the presence of magnetic field together with differential rotation. So differential rotation is typically present in the merger remnant, and during merger, magnetic field is usually amplified by MHD instabilities. So here MHD instabilities means that Kelvin instability and magnetic rotational instability, and so on. And then due to the this instability, turbulent is excited, and then effective viscosity are also induced. And also due to the magnetic field amplified, and then purely MHD effects are important for evolution of the post-merger elements. And so anyway, due to this effect, mass ejection occur from the post-merger remnant, in particular from a disk or torus. And what is interesting for long-lived neutron star, so fairly small total mass binary neutron star case, so ejecta mass is likely to be very high, because in the absence of a black hole at the center, it's not very easy to fall in, for matter to fall into the neutron star, because to fall into the matter, for the matter to fall into a neutron star, we have to remove the some energy, because the neutron star has binding energy, typically about 10% of the neutron star mass. So we need some cooling process, but during cooling, time scale, it's not possible for matter to fall into the black hole. And then as a result, ejecta mass fraction increase, and so this increased to about 0.5% to 10% of a solar mass. And in addition, for determining the ejecta properties, weak interaction physics, including neutrinos irradiation, is the key. So I will a little bit talk about this from now. So anyway, this is I'll talk about the basic evolution process for disk. This is determined by a neutron cooling and effective viscosity. So anyway, after the merger, everything is very hot and dense. And of course, the density of a disk is also dense and hot. And in such phase, also due to the magnetorotational instabilities, this fluid behave effectively as a viscous fluid. So then viscous angular momentum transport and viscous heating occur. However, viscous heating is fully consumed by the neutrino cooling in the early phase, because temperature is very high. In such phase, even if heat is generated by viscosity, it is fully emitted by neutrinos. And in such case, no viscous mass ejection occur. Of course, even in this phase, MHD process like Bramford-Penn effect, magnetic centrifugal effect, could play a role, but for this condition, we need a global magnetic field line. And it's not clear that the global magnetic field line, very strong global magnetic field lines are present from the beginning. So I'll talk about later about these topics. However, even if the viscous heating is consumed by the neutrino emission, even in this case, the viscous angular momentum transport occur and the disk expand. And that means that density of disk and the temperature of disk decrease gradually. And then after viscous angular momentum transport timescale disk expand, and eventually Newton luminosity decrease. And then viscous heating can be fully used for disk expansion and then mass ejection setting. This occurs typically, so according to the numerical simulation, so after the maximum temperature of disk decrease below about 3 MeV. And this time scale is fairly long. So this is so approximate estimate for viscous angular momentum transport time scale. And typically it becomes about several hundred milliseconds to seconds. So that implies that we need a very long-term simulation. So for dynamical mass ejection, we only need to simulation for about several 10 milliseconds, but for studying the post-merger mass ejection, we need a simulation for more than 1 second.
Shibata-san.
Yes.
Quick question.
Yeah.
The number of 3 MeV, what does this number come from?
Yeah, so this number is, so I'll talk tomorrow in the next slide. So,
okay.
So why of disk is determined. Anyway, so this is the evolution process of the disk chemical composition for disk. So anyways, as I said, that initially disk density is about 10 to 11 gram per cubic centimeter, and the temperature is roughly speaking 7 to 8 MeV. And in the presence of neutron stars at the center, temperature could be higher than 10 MeV. And anyway, in such case, so beta equilibrium, including neutrinos, are established. So this process is established, and Y is determined in this process by this. So by equality of the chemical potential. And in the typical scenario, so neutron reaction decouple fast. So this process decouple fast. Still, electron and positron capture process proceed because of high temperature. So like this. And however, after the temperature drops, so this process also decouple. And this temperature is about 3 MeV. So the reason is that for this process to occur, so positron is necessary, and this means that the positron electron pair productions are necessary. So that means that the temperature should be higher than 1 MeV, roughly speaking. So maybe 3 MeV is a little bit higher, but very close to 1 MeV. So I think that this decoupling is due to the mass of the electron and positrons. This is my naive understanding. Is it okay for you?
Thank you very much.
And anyway, so after temperature drop below 3 MeV, mass ejection occur. However, in this phase, so density of a disk is maximum density of disk is already 10 to 9 gram per cubic centimeter, and so that means that electron degeneracy is not very extremely high. And this is a reason why at the mass ejection, neutron, so disk is moderately neutron rich. And I'm with the terminology of Y, so it's become about 0.3. So, and with this fairly large value of Y, so heavy element elements like gold and platinum are not produced a lot. Also, lanthanide are not produced a lot. So this is our process nucleosynthesis calculation for the case that major remnant is a massive neutron star plus disk. So this is based on the 3D radiation hydro simulation and 2D viscous hydrodynamic simulation. And solid line shows the elemental pattern for the post-merger ejecta. This is atomic mass number, and this is a fraction mass. And for the post-merger ejecta, so first and the second peaks with a mass number about 100 and 130 are efficiently produced, but so third peak are not efficiently produced. One exception is that if we assume we employ the very extremely high viscosity, this is produced, but this is so I think that this is not very realistic. And dotted line shows a dynamical ejecta distribution, and so from dynamical ejecta, so third peak element and produced and the amount is as much as many as the second and the first peak. However, so as I said that for the massive neutron star formation case, dynamical ejecta mass is fairly small, 10 to minus 3 solar mass or something like that. By contrast, post-merger ejecta mass become 5 to 10% of the solar mass. So this post-merger ejecta become a majority, and the dynamical ejecta become a minority. And as a result, from this system, mainly first and second peak component are produced. So I mean that from this system, so it's not very easy to reproduce a solar abundance pattern. Here, black dot denotes solar abundance pattern. This is one conclusion until last year. However, this calculation, we don't take into account other MHD effects, and so the natural question is that other MHD effects important for the evolution of remnant massive neutron star plus disk. So this could be because remnant neutron stars are rapidly and differential rotating, and not only the disk but also in the neutron star. Magnetic field amplification could occur, and this could affect the ejecta property. And anyway, so question is that which MHD effects are important and the time scale. And so the important thing is that if time scale, so mass ejection time scale is shorter, YE becomes shorter. So the reason why in this figure, so for extremely high viscosity, we have this kind of the result is that due to the very rapid mass ejection. So if mass ejection occurs earlier, then so YE doesn't increase significantly in the disk, and then so we could obtain the large amount of the heavy elements. So anyway, so to explore the possible effects of MHD process, we performed a resistive MHD simulation with a dynamo term for remnant neutrons plus disk. So anyway, so I think that many people in the MHD physics believe that the alpha omega dynamo is likely to be the key player for magnetic field amplification. For example, for accretion disks, so alpha dynamo is induced primarily by MRI, and this could play an important role for amplification of magnetic field and the subsequent evolution of disk. But for neutron star, it's not very clear. So as I said, also for neutron star, we have differential rotation, and alpha omega time. Omega here, alpha means that alpha parameter of dynamo, and omega means that this means that presence of the differential rotation. And so neutron star has a differential rotation, and alpha omega dynamo may be induced as well due to the winding. So winding occurs in the presence of differential rotation, and some subsequent MHD instabilities such as Taylor instability and Parker instability. And also convection may be important in the remnant neutron star. But the first principle numerical simulation is extremely difficult. We need a high resolution 3D MHD plus Newton physics and so on. So we here employ a very phenomenological approach and explore the possible effect by amplified magnetic field. So this is a basic equation for the resistive MHD plus dynamo. So here, so E nu is densitized. This is E is electric field in the rubber frame, and B is magnetic field in the rubber frame, and this E and B are densitized. Gamma is a determinant of the 3 metric. And this is a basic equation of the electric field and the magnetic field, and the J is a current density, and the current density is written like this. So this is composed of the bulk charge flow, and this alpha is a Laplace function. The sigma c is a conductivity, and this is the so-called electric field term in the fluid rest frame. And so here, so this is a usual, this for these two terms usually appears in the usual resistive MHD. And here we add this term. So this term is associated with a magnetic field in the fluid left frame. And alpha D is the so-called alpha parameter for dynamo. And so anyway, so we perform the simulation adding this term. And the reason is that with this, so magnetic field amplification occurs even in arc-symmetry. So in arc-symmetry, we have an anti-dynamo theorem, and this means that toroidal field is amplified in the presence of poloidal field. However, poloidal field is not amplified even in the presence of a toroidal and poloidal field. So, but with the presence of alpha D, even in arc-symmetric simulation, so magnetic field is amplified. So anyway, this is a very phenomenological so prescription, but to explore possible magnetic field amplification effect, this is a very simple prescription. And we have the following questions. What is the typical value of alpha D and sigma C? So for this, Brandenburg is a specialist, and he wrote a very interesting review about 15 years ago. So, and so using this isotopic turbulence theory, we can estimate the alpha and the sigma, assuming that velocity fluctuation is determined by some magnetic rotational, or some magnetic field MHD effect. Then we can find that this parameter is approximately 10 to minus 4. So note that this value approximately agree with the previous local simulation result. And also eta is a resistivity that determined from the conductivity is also written like this. And this becomes this parameter for remnant neutron star and remnant disks. So yeah, anyway, so we use these values. So assuming that dynamo is determined by the magnetic hydrodynamics process. And also according to the dynamo theory, so gross time scale is determined like this from these parameters, in addition to this differential rotation degree. S is a differential rotation degree with this pi is a cylindrical radius. Then we found that the gross time scale of dynamo is about 20 milliseconds. And so magnetic field is likely to be amplified from the 10 to 12 Gauss to 10 to 15 Gauss or something like this. So that means that for full amplification, perhaps the time scale is about 10 times longer than 20 milliseconds, and the typical time scale becomes 200 milliseconds. So this time scale is indeed agree with the latest simulation in the result of a latest simulation for black hole accretion disk. So anyway, so afterward, this is a phenomenological approach. So we need to check. So for checking, so we performed first simulation for disk around the black hole. And also then, so we performed the simulation for neutron star surrounding, so disk surrounding a neutron star. And in the following simulation, so we always use axial and z-plane symmetry. So for this prescription, we don't need a 3D simulation. And so if we employ the initially poloidal magnetic field, we often have the so wrong result. Wrong result means that in the presence of a poloidal field initially, so winding play a very important role. So to avoid such an artifact, so we start a simulation from a toroidal field, purely toroidal field. Okay, so let me show this first the result for the black hole plus disk case. In this simulation, we employ the temp solar mass black hole with a spin parameter 0.8 and disk mass is 0.1. And dynamic parameter is these parameters, these values. So this is a typical value according to the estimate due by the isotopic dynamic theory. So here, so density, temperature, and entropy per volume, and electron fraction. And here, so you can see the disk, initial disk radius is about 200 kilometers. So anyway, so in the first 200 millisecond magnetic field is amplified, then so mass ejection occurs. Yeah. And after the establishment of the turbulent state mass ejection gradually occurs. It's too early, so it's not very easy to find the details. But anyway, so this evolution process is very similar to the viscous hydrodynamics simulation and also 3D MHD simulations. So this is a magnetic profile, so history of the magnetic field amplification. This shows the electromagnetic energy, and this shows the ratio of the electromagnetic energy to kinetic energy. This is a time in unit of a second. So as I said, initially spending several hundred, roughly speaking, 100 milliseconds, so magnetic field is amplified. And then eventually saturation is encountered. Then so turbulence occurs inside disk, and then matter is ejected from the disk, and also matter fall into the black hole. Then so electromagnetic energy decreases due to the mass ejection, and matter inflows the black hole. This is a ratio of electromagnetic energy to kinetic energy. So as we often see in this kind of simulation in MHD, after the amplification, this value relaxes to the between 0.1 and 0.01. This shows that turbulence is established, and accretion and mass ejection become in the steady state. So we have many curves. This is a curve with different parameters. So we employed several parameters for alpha D and sigma C, but irrespective of the parameters, qualitative trend is very similar. Of course, for higher value of alpha D, dynamo effect is more important, and for higher value of sigma C, so dissipation effect is less important. And then so for higher value of alpha D or sigma C, energy is drops earlier. But irrespective of these parameters, this ratio is always roughly speaking 0.01. So this means that I mean that with this prescription, approximately usual often performed ideal MHD simulation result reproduced. And this is a quantity for ejecta. Here, so black curve is a viscous hydrodynamic result, and others are MHD with dynamo with several choice of alpha D and sigma C. This is a mass outside the black hole. This is a mass already falling into the black hole, and the dotted curve shows the ejecta. And let's focus on the ejecta. So this black curve shows the evolution of ejecta, and so because the matter outside black hole relaxes about 20% of initial mass, and so ejecta also relaxes to the about 20% of the initial mass. And so for MHD with dynamo, so this mass ejection time scale is a little bit earlier. Perhaps this is due to the purely MHD effect. So in viscous effect, only viscous effect play a role for mass ejection, but for MHD simulation, not only the effective viscous effect, but also the purely MHD effect play a role, and the mass ejection time scale become shorter, but still so qualitatively trend is very similar. I mean that after several hundred milliseconds, so neutron cooling become less efficient, and then so mass ejection occurs. And this is a special entropy by volume, and this is a YE, and this is a velocity of average velocity of ejecta. So for MHD simulation, average value of YE is slightly smaller. So this is a viscous result, and these are MHD result, but difference is only 0.05, and so with MHD effect, so viscous effect is approximately reproduced, and also velocity is slightly higher. So this shows the evidence that additional MHD effect play a role for enhancing the ejecta velocity. But still, so ejecta velocity is about typical 10% of the speed of light, and for ejecta, for viscous case, it's about 5%, but the difference is not very huge. And also, in previous ideal MHD simulations, so ejecta velocity become this order of magnitude, and so this result shows that our phenomenological approach approximately reproduce the ideal MHD approach result. Okay, so this is a evolution of toroidal field line and toroid field strength, and you can see the well-known butterfly diagram. So this is natural consequence of the incorporating dynamic process. So finally, I'll show the result for remnant neutron star plus disk. So here, first we performed the neutron star merger simulation in 3D. So choosing the 1.35 solar mass model. And then we performed axisymmetric simulation using a merger remnant for 3D simulation. So this is a result for the 2D, so MHD simulation. So this is the initial condition resulting from the 3D simulation. So again, density, temperature, and entropy varying and YE. And because in this simulation, initial condition has a dynamical ejecta. As a result, velocity vector is outgoing. And as in the previous case, so mass ejection occur primarily from the disk due to the excitation of the amplification of magnetic field and the resultant turbulent effect. However, one very important difference appears. So this is electromagnetic energy as a function of time. So as in the previous case, magnetic field is amplified due to the dynamic effect, and then subsequently decrease. But this decrease curve depends on the parameter of sigma c, because the conductivity determines the dispersion time scale of magnetic field, and dispersion time scale of magnetic field is written like this. And so for larger sigma c, dispersion time scale is longer, and so lambda is a wavelength of the dispersion mode. And here, neutron star radius is a maximum value of the lambda, and so that means that if, for example, this become very short for lambda equal 10 kilometer, magnetic field dissipate in the neutron star soon. And in this choice of the sigma c, magnetic field doesn't dissipate soon. Doesn't dissipate soon in neutron star, and then magnetic field energy is preserved to be high. But for other cases, magnetic field is dissipated in neutron star soon, but magnetic field in the disk is preserved, and then this magnetic field strength is determined by the magnetic field in the disk. For this case, magnetic field in the neutron star determines the total value of EV. But anyway, for this case, you can see that the curve is very similar to the accretion disk case. So that means that mass ejection primarily occurs from the disk. But we have additional effect. So this is again ejecta mass, velocity, and entropy per baryon and YE. So black curve shows the viscous result, and the dotted curve shows the low resolution result. But here, please neglect the low resolution result, dotted curve. And anyway, ejecta value is very similar, irrespective of the dynamic parameter. However, time scale is different. If sigma c is large and the dispersion time scale long, so mass ejection occurs very quickly. comparing with the viscous case. This is also the case even for the smaller variable sigma c. This reflects the fact that we have the magnetic effect, purely magnetic effect play a role for mass ejection. Indeed, due to the presence of a purely magnetic hydrodynamics effect, ejecta velocity is significantly enhanced, like this. So, for example, for extreme case, ejecta velocity become about 50% of the speed of light. I don't think that this is a very realistic, but anyway, so in the presence of a very strong magnetic field and the long-lived magnetic field, the ejecta velocity is significantly enhanced. Also, entropy variance enhanced. The reason is very simple. So, so by dynamo action, magnetic field is amplified, and then some of the field loops are ejected from neutron star. And then global field with high field strengths are developed. And then some of the field lines have anchor at the neutron star. And then in such case, so because the neutron star is more rapidly rotating the disk in this case, then so neutron star swings magnetic field very efficiently. So then so magnetocentrifugal force associated with the neutron star plays a significant role for enhancing the ejecta and accelerating ejecta. This occurs if a neutron star magnetic field is preserved for a long time scale. And this is a reason why the velocity is enhanced. But this, reduced to the one interesting prediction. So in the radial light curve, because the ejecta energy is very high, kinetic energy is very high, and the interaction between the interstellar matter is also enhanced. This is predicted radial light curve for this model, and if dissipation time scale of a magnetic field inside neutron star is fairly long, then so radial luminosity can be quite high. So this is a unit of microjansky, and this shows that peak luminosity can be about millijansky. So this is a result at a distance of 200 megaparsecs. So this can be easily observed using the currently available observational radio telescope. So this is one prediction. By contrast, electron fraction for the ejecta don't change from the viscous hydrodynamics result. So for viscous hydrodynamics result, please see the black curve. For MHD case, so small y component increases slightly, but essentially, so this trend doesn't change so much. As a result, so in this scenario, again, so heavy R process elements are not produced efficiently. So then, this is a conclusion from our study. First important topic is that ejecta velocity could be significantly enhanced if in the presence of a massive neutron star with strong magnetic field, which is preserved for more longer than 100 milliseconds. In this case, kinetic energy of ejecta can be 10 to the minus 50 ergs due to the magnetocentrifugal force associated with the neutron star. So the one prediction is that for the case of neutron star, long-lived neutron star scenario, bright area emission for these radio waves could be observed. For the case of GW7170, we don't have no early radio shining, so this may mean that EOS may be soft. I mean that, so in this case, black hole may have to be formed soon after the merger. And finally, so for irrespective of the viscous simulation or MHD simulations, so main component of ejecta has a high YE. So high means that about Y equal 0.3. In such case, so light elements are overproduced, but heavy elements are not produced enough. So this doesn't agree with the solar abundance pattern. So that could imply that neutron star to long-lived neutron star may be a minority in nature. So that's all. Thank you very much.